Okay, we are up to section 2.5, maximum minimum problems, business, economics, and general applications. So now we are really into the application here of the calculus. And um, these problems can take a little bit longer, so we'll probably do this section in a couple of videos, maybe three. I'm hoping to get it in two. We'll see how it goes. Okay, and as you can see, there's a lot more space and for each problem. That's because they are word problems and they do take a little bit more work. So we're going to kind of try and take these slow. Our objectives are simply to solve max and min problems using calculus. Vocabulary, maximum minimum problems. We've actually seen maxes and mins before. And the last problem that we're going to do is an inventory problem. So we'll go over some things there because some of that might be kind of new. So in the last section, we practiced finding the absolute largest of a function that we can get, or the absolute smallest of a function. And this kind of information, this is actually what really is useful in practical applications. As you can expect, in businesses, a lot of times people want to know how to maximize something, specifically profit. You'd want to maximize your profit as a business. Or you might want to minimize the material that you use in order that you can maximize your profit. So there's a lot of different things that go into maximizing and minimizing. So let's go ahead and start with example number one. And in a lot of these examples, some kind of a sketch is really going to be helpful. So you'll see me sketch a lot on this one, on this particular unit. All right, example one. A hobby store has 20 feet of fencing to fence off a rectangular area for an electric train in one corner of its display room. The two sides up against the wall require no fence. What dimensions of the rectangle will maximize the area? And then what is the maximum area? Okay, a lot of times in these problems, you're not going to necessarily catch everything you need to catch right away. So you might have to go back and read it, and sometimes you have to read it and read it and read it until you actually understand it. We're going to go back and kind of pick this apart piece by piece. So the first thing that we're told is we have 20 feet of fencing. Okay, so that's how much fencing we have to deal with. We want to fence off a rectangular area that we can put this electric train set in. So I'm sure you've seen those kind of things before if you've ever gone to like one of those hobby places. But it does say it's in the corner of the room. So we're going to have a corner of a room. So here's like the corner of the room. And then we're going to use our fencing. This is the two sides up against the wall. Obviously, you don't want to fence up against the wall. It makes no sense. But we're going to use the fence here in green to fence off some kind of a rectangular area. And then, you know, inside here, you've got your toy train set or whatever. You got your choo-choo train that's going around here. This is really horrible, choo-choo train, but you get the idea. Anyway, there's our choo-choo train. Okay, so we're going to use the green area as our fencing. Well, we've got 20 feet of fence to deal with. So we know that that green, I should not have probably put the track in green, but the rectangular part of the green is how much fencing we have. That totals 20. It says, what are the dimensions of the rectangle that's going to maximize the area? So that's a key. It's telling us that we want to maximize area. Okay, that's important. That means we need to know how to find the area. Well, it's a rectangular area. So area is simply length times width for a rectangle. Okay, so what we need to come up with now is we need to come up with something that gives us these dimensions. Well, typically, if you want to use, I mean, we can use L and W. There's really no problem with doing that. So let's just call this the L and that the W. I also know that the total amount of fencing, which is going to be the length plus the width, because that's the total amount of fencing, the length plus the width is 20, because they told me that's how much fencing we have. So what we need to do is we need to solve this equation right here, solve this one right here for either L or W. In this case, it doesn't really matter. In some cases, it's going to matter because it's going to make things easier, but in this case, it doesn't matter. So I'm going to solve that equation for L just by subtracting W on both sides. So we're going to get that L equals 20 minus W. Okay, so now what we're going to do is what we can do is we can now create this equation for area in terms of one variable, and that's the important thing. We need to get it down to one variable. So let's see, we're going to have L, which is now 20 minus W, times W. So that was L, and that's W. But now it puts it down into one variable. So now all I have to do is distribute my W, so I get 20W minus W squared. Okay, why is that important? Well, now it's because I have one variable, I have one independent variable. Now what I can do is I can go ahead and take a derivative. I'm going to take a derivative because we are trying to find the max or the min of something. We're trying to maximize the area, so we need to find the derivative so that we can find the critical values. Once we find the critical values, we can test the critical values and the endpoints to find the absolute maximum. So let's go ahead and do that. So the area prime is going to be 20 minus 2W. And I need to set that equal to 0 to find its critical value. So then we'll solve that for W. So we're going to get that 20 equals 2W, adding 2W to both sides. And then we'll divide by 2, so we get that 10 equals W. Well, that's the only critical value that I have. So let's go ahead and test it using our second derivative. And the second derivative is -2. Well, the good thing is the second derivative, there's nothing for me to plug anything into. The second derivative is negative no matter what. That indicates that we had concavity, which is down, which actually indicates that no matter what I have, because the concavity is down, my critical value would create a maximum. Okay? So I do know that that 10, this 10 value right here, is going to be a maximum. Okay? Now, if I really wanted to be prudent here, I need to check my endpoints. Well, I can either use 0 feet of fencing or I can use 20 feet of fencing. That's the only other options. Those are the endpoints, because you can't go outside of your domain since we have only 20 feet of fencing to deal with. Well, if you were to put a 0 or a 20 back into this equation, you're going to get 0. You're going to have an area of 0. And that really should make sense, because if you use 0 foot of fencing for 1, that means that your entire fence is going to be on one wall. If you use 20 foot of fencing, it just means that your entire fence is going to be on the other wall. Without actually physically drawing all that out. Hopefully that makes sense. So we do know that 10 here is going to be our max, or it's going to give us our max. Now it does want the maximum area. Well, the maximum area is going to be when we use 10 for W. Let's just go ahead and plug it back in. So the maximum area is 20 minus 10 times 10. 20 minus 10 is 10. 10 times 10 is 100. So our maximum area, let's see, what are the units? They're feet, and it's squared. Max area is 100 feet squared. And there we go. All right, as you can see down here at the bottom of the page, it gives you some of the strategies, which I've kind of already highlighted anyway. It says, read the problem carefully. If relevant, make a drawing like we did. I like to add to step 1, read, 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 read. You're going to have to read it as many times as it takes for you to actually understand what the problem is asking. Sometimes that's the most difficult part. Write down formulas involving constraints of the problem. Okay, that's what we did when I wrote down the perimeter portion and the area portion. Make sure that you write the problem in terms of one quantity to be maximized or minimized. In our previous example, that was the area. Okay, they call it Q here, but you write it as whatever you want to, as far as like if it's area or perimeter, whatever you're trying to maximize. It usually tells you that in the problem. Use substitution to write the formula for Q in terms of one variable. That was important. That's why I used that perimeter portion to solve for, in the case that we did up above, L, and then we back substituted that into the area problem to get down to one variable W. And then use techniques developed in the previous sections to find the max and min, and make sure that you're on the appropriate intervals. Like I said, we could only go from 0 to 20, although those didn't make sense in this case, but make sure that you're on your domain. All right, let's go ahead and take a look at problem 2, and then we'll probably have to come back with a second video after this one. Okay, Mendoza Manufacturer specializes in food storage containers and makes a cylindrical soup can with a volume of 250 centimeters cubed. the cost of the material for two circular ends is 0.0008 dollar or cents per centimeter squared, and the cost of the material for the side is 0.0015 centimeters squared. What is the dimension, sorry, what dimensions minimize the cost of material for the soup can? And then what is the minimum cost? Again, this is a perfect example. You would want to minimize the cost of manufacturing this soup can as a manufacturer. So this is what we're looking at. So we're going to have to definitely do a little bit of sketching here. A soup can. We're going to assume it says in the italic section that there's no extra lip and stuff. We're just basically going to say that we have a cylindrical can. So you're going to have your can, you know, that looks something like this. You don't have to be the best artist, which I certainly am not, to get this, but you know, you kind of want to give yourself an idea. So there's our soup can, and here's the biggest thing. What you have to do now, we're trying to minimize the cost of the outside of the can. The can itself has three different pieces we're going to look at. We have the top of the can, we have the bottom of the can, which is kind of hidden, and then we have the outside face of the can. Okay, what you have to do here in order to figure out how much material it is, you kind of have to open up the can. This is actually what's called a net. We're going to take a three-dimensional figure and kind of create a two-dimensional flat piece so we can see how to do this. So if we were to take that same can and we were to open it up, so we're going to take the top, we're going to leave the top connected. It's almost like if you took a can opener and you open the can all the way around, but not quite fully taking the top off. You could bend the top up, so the top would be kind of sitting like this. And then what you're going to do is you're going to take and you're going to cut the can. You're going to cut it straight down the middle on the other side, like this. You're just going to cut it straight down there. Take some shears or something and cut it, and then you're going to open it up. Well, if you think about it, if you open that up, what it's really going to look like is this rectangular piece right here. If you were to open up a can and you open the whole thing, it's just going to look like a rectangle. And then you have the bottom. We do the exact same thing to the bottom we did to the top. It's just going to be sitting there like that. So that's kind of a two-dimensional drawing of a three-dimensional figure if we open it up. Again, it's called a net. So what we need to do is we need to figure out the areas of these pieces so that we can figure out what the minimum cost is, because we want to minimize the material used here. Well, this piece right here is a circle. This piece right here is a circle, and they are really the same thing. Well, a circle's area is pi r squared, and pi r squared. Okay, this piece over here, this rectangular piece, this is the part that's going to be a little bit different. This piece up here, we know that the area of a rectangle is length times width. Length times width. Typically, we'll call the longer piece the length, so we'll call this piece up on the top the length and this piece the width. But if we go back to the can, we know that this piece right here, this piece, corresponds to this. It's nothing more than the height of the can. So we're going to call W H. And then we got to come up with something for the length. Well, the length is really this piece of the can. If we start here and go all the way around here and open it up, that's really the top. That's this piece right here. Well, if you go all the way around the outside of a circle, that's the circumference of a circle, which is 2 pi r. So I do know that this piece is going to be 2 pi r. So I know that all of the area is all of these things added up. So I know that my area is going to be, I've got a pi r squared on the top and a pi r squared on the bottom, so I've really got two of them. And then I've got this 2 pi r times the height, h. Okay, we still have not gotten this down into one variable. So we need to come up with something else that tells us that we can get this to one variable. Well, they gave us one additional piece of information that we're going to be able to use. They told us the volume of the can was 250 centimeters squared. So the volume, which of a can or a cylinder, is going to be pi r squared times the height. That is the volume of a cylinder. Well, I know that the volume is 250. They gave that to me. So 250 equals pi r squared times the height. That does not look like an equal sign there in the middle. Let me change that real quick. There, that's better. So now what I can do is I can solve this equation either for r or for h. Well, it's much easier to solve for h, and that's going to allow me to plug that into the h over here, and everything will be now in terms of r. So let's go ahead and do that. I'm going to scroll this down now because we're pretty much down to just doing the math now. So we're going to solve the volume equation for h. We're going to divide both sides by pi r squared. So we get 250 divided by pi r squared equals h. I'm going to take all of that and I'm going to plug it into the h up in my area equation. So my area equation now becomes 2 pi r squared plus 2 pi r times my height, which is now 250, divided by pi r squared. That's h. Okay, I'm going to do a little bit of simplification here before I start adding in extra components. So let's see. We're going to simplify. The pi's here will cancel out. One of these r's is going to cancel out with one of those r's. And I can multiply the 250 on the top there. So it looks like we've got 2 pi r squared plus 500 over r. And now we're to the position where we can actually try and maximize or minimize the area. But I'm really not just trying to max or minimize the area. I'm trying to minimize or maximize the cost. What it tells me is that it costs a certain amount of money per the top and per the side. It looks like we're using this much right here for the top and the bottom. That's the circular ends. And then it looks like we're using this amount for the side. So I have to multiply that by each one of these pieces before I can go ahead and take the derivatives. So we're going to multiply the top and the bottom. That's the 2 pi r squared by 0.0008. So let's go ahead and write that in. So the area now becomes 0.0008 times 2 pi r squared. And then, what was it? 0.0015 was the sides. So 0.0015 times 500 over r. So let's go ahead and simplify that, and then we'll be able to take a derivative. If we multiply 0.0008 times 2, we get 0.00, what is that, 16? Yeah, 16 pi r squared. And then if we multiply 0.0015 times 500, that gives us 0.75 over r. All right, one more thing I'm going to do, and then I'm going to take the derivative. 0.0016 pi r squared, that's going to stay the same. I'm going to rewrite this other one as 0.75 r to the negative 1. It's just going to make it easier to take a derivative. We can put it back into a fraction later. All that stuff was the big setup. A lot of work there for the setup. So let's go ahead now and take the derivative. The derivative is going to be, let's see, 0.0016 times 2, bringing the 2 out front is 0.032, I believe, pi r. Yep, that looks right. And then minus 0.75 r to the negative 2 power. And we want to find the critical values for r, so we're going to set that equal to 0. So we're going to get 0.0032 pi r minus 0.75 over r squared equals 0. We'll add 0.75 over r squared to both sides, Multiplying both sides now by r squared, we get 0.0032 pi r cubed equals 0.75. I'm going to have to definitely do this next part with the calculator. Now I have to divide both sides by 0.0032 and pi. So pi r cubed, let's see, what is 0.75 divided by 0.0032? 0.75 divided by 0.0032 is 234.375. None of these numbers are going to come out to be really nice. 0.375. Now I have to divide by pi, and then we're going to have to take the cube root. I'm going to try and do all that at once here. If I divide that by pi, and make sure when you do the division, you use your pi button on your calculator if we're doing a decimal approximation, which we are going to get here. And then I've got to take the cube root, which is really the same thing as raising it to the 1/3 power. So any way you want to do that, as long as you come up with the right thing. So it looks like r is going to be approximately 4.21. So that's going to be our approximate radius. And this should minimize it. We can go ahead and take a second derivative. And the second derivative here, I'm actually going to go from this piece right here. To take the second derivative is going to be 0.0032 pi plus, let's see, 0.75 times 2 is going to be 1.5 r to the negative 3. This whole thing right here is always going to be positive for any positive value I plug in. So because this is positive, that means it's going to be a concave up, which means it is going to be a minimum. So this right here did minimize our material for our soup can. So let's see. This was done in centimeters. So that radius is going to be in centimeters. And then it says we actually want to find out what the minimum cost is. I have to apologize because what I found there was the area. I think I labeled these wrong. So we're going to go back and correct this real quick because I don't like to leave things wrong. Everything was good down to here. This was all area. After that, now we actually have a cost function. So I'm going to erase these. And instead of A's, we're going to put C's in their place. So that's a cost function. C prime now is the cost function's derivative there. Okay, there we go. Now that looks good. All right, so our actual cost at the minimum value, the minimum cost here is going to be, we can go probably to the most simplified version of this, which is 0.0016 pi. Our R value that we just found was 4.21 centimeters squared. And let's see, where am I? Plus 0.75 over that. Plus 0.75 over 4.21. So our approximate cost, which is going to be the minimum cost, is going to be what we get when we plug this in the calculator. And that comes out to be about 0.27 cents. It's 0.267. I'm rounding 0.27 cents for the can. All right, that's plenty enough for those. We'll come back and do a second video, and then we'll see if we need to do a third.